Welcome to the learning curve. In this lesson, we'll be looking at probability. I'll be doing an illustrative lesson which helps to bring out some of the fundamental rules that are applied in calculating probability. Here we are told in this question that a study of traffic violations and drivers who do not wear seatbelts produced the following data. The data set is divided as follows. The column variables are speeding violations in the last year, which is A, no speeding violations in the last year, which is B, persons who wear seatbelts, which is C, and persons who wear no seatbelts, which is D. Before we even calculate the probabilities for this from this table, one of the first things you want to do when you're given a table like this to calculate probability from is to determine the column totals and the row totals, and hence use that information to determine the total number of observations or sample size. So the first thing we're going to do here is to work on the column totals. So let's work on the number of persons, the total for the number of persons who had speeding violations in the last year, which is 23 plus 45, and 23 plus 45 here is going to give us 68. So this 68 means that there were 68 persons who had a speeding violation in the last year. Then we go to the second column. Let's take the total for the number of persons who had no speeding violations in the last year, which is 123 plus 67, and that gives us 190. Next, we're going to take the total of 190 plus 68. When we take the total of 190 plus 68, we get 258. And that 258 represents the total number of observations or sample size for this data set. Let's now look at the row totals. So let's first look at the first row here, the number of persons who actually wore seatbelts. So we're going to add 23 plus 123, which is going to give us 146. And then we're going to add 45 and 67. So 45 plus 67, which is equal to 112. That's 112. Now, when we add 112 plus 146, we will get 258. So the row totals must add to the same value as the column totals, if indeed the additions have been done correctly. So that you can use as a blueprint to determine if you have added the values correctly. The row totals must add to the same figure as the column total. So this 258 figure is a very important figure. It represents the sample size or total number of observations. So this is our sample size. Sample size or total number of observations. The sample size is generally represented using the symbol S, sample size. So this 146, of course, means that there were a total of 146 persons who were wearing seatbelts. The 112 means that there were 112 persons who were not wearing any seatbelts. Let's look at the scores within the table, which represents the intersection of two variables. This 23 here represents 23 persons who wore seatbelts and had a speeding violation in the last year. So that's helping us to understand the table here comprehensively. This 45 represents the number of persons who did not wear seatbelts and had a speeding violation in the last year. This 123 represents the number of persons who wore seatbelts and had no speeding violation in the last year. And the 67 here represents the number of persons who did not wear any seatbelts and also had no speeding violation in the last year. So all of these figures represents the intersection value for two variables. So number one, we're asked, what is the total number of persons in the sample, which we've already determined the total number of persons in the sample, which we could say is n, or we could say S, the sample size, is equal to 258. So this is the number of persons in the data set, or we could say number of persons in the sample. So let's write that. We're going to say here we're going to say the number of persons in the sample. So I'm going to say NS, number of persons in the sample. So that's 258. In the next problem, we're asked, what is the probability that a person had no violations in the last year? So what we're going to write the probability statement here first and foremost. This is the probability that the person had no violations in the last year, which is the probability of B, since B is being used as a symbol for no speeding violation. So basically we're asked to find the probability of B. So the probability of B would basically be the number of observations in B divided by the number of observations in the entire sample space. In all cases except when it is a conditional probability problem, we will divide by the total number of elements in the sample space to derive the probabilities from tables like these. So here we will get the number of persons in B divided by the number in the sample space. The number of persons in B is 190. That is the number of persons who had no speeding violations in the last year. So that will give us 190 divided by the total sample size of 258. So the probability that a person had no violations in the last year is 258. When we are asked to calculate the probability of a single event, this is called a marginal probability. So since we were asked in this case to calculate the probability that a person had no speeding violations in the last year, that is a single event, no speeding violations. And therefore this is an example of a marginal probability. When we simplify this into a decimal to two decimal places, this will be 0.74, or a 74% chance that a person had no speeding violations in the last year. And that takes care of number 2. Let's go to number 3. Number 3 says, what is the probability that a person had no violations in the last year, given that the person wore a seatbelt? Now, this expression, given that, is a very important statement in this question. Once you see that statement, given that, or if, or any expression that connotes that same meaning, then you know we are dealing with conditional probability. In other words, we're asked to find the probability that a person had no violations, which is B, given that, in other words, on the condition that they wore their seatbelts. And wearing your seatbelt is represented using the symbol C. In situations where we are computing a conditional probability, like in number 3, what we must do is to ensure that what is used as a sample size is the number of observations in the event that is relied on. And the event that is relied on in this case is the event that comes after the given that, which is persons who wore a seatbelt. So let's demonstrate. Let's first write our probability statement. So the probability statement for this conditional probability problem is the probability that there will be no violation, the probability that a person had no violations, which is B, given that, which is what this slash means, given that the person wore a seatbelt, which is used, the symbol C is used to represent. So this is the probability statement, the probability of B given C. In other words, the probability that a person had no traffic violations, which is B, slash, which means given that they were wearing a seatbelt, which is C. And the formula for conditional probability here would be the number of observations, N here meaning number, the number of observations in the intersection of B and C. So this is the probability of B intersects C. But with conditional probability problems, we do not divide by the number of observations in the sample space as we did in question 2 here. We'll divide by the number of observations in the event that is relied on, which is the event that comes after the slash here, which is C. So the number of persons in C, which is the number of persons wearing a seatbelt, is this here, the total for the column seatbelt, which is 146. So this is what the conditional probability formula for this problem would look like. The probability of B given C would be equal to the number of observations in B and C, all divided by the number of observations in the event that is relied on, which is C. So this would be equal to the probability, the number of observations in B and C, which is the number of persons who had no violations and also wore a seatbelt. That's what the numerator of the form of the equation here is saying. The number of persons in B and C simultaneously or together, which is the number of persons who B had no speeding violations and also wore a seatbelt, which is the 123. This 123 represents the number of persons who satisfied two conditions. That is the condition of wearing a seatbelt and having no speeding violations. So the numerator would be 123, and we're going to divide that by the number of observations in C. That is the number of persons who wore seatbelts, and that's 146. And this is the probability that a person had no traffic violations, B, given that they wore their seatbelts, which is C. When we simplify this fraction, 123 divided by 146, we get 0.84, or in other words, 84%. So this is 0.84 or 84%, which means that there's an 84% chance that a person had no violation in last year, given that the persons wore a seatbelt. In other words, on the condition that a person wore a seatbelt, what is the probability that they had no speeding violations last year? And that is 84% as calculated here. That takes care of that. And on to the last problem in this illustration. What is the probability that a person wore a seatbelt or had no violations in the last year? What is the probability that a person wore a seatbelt or had no seating violations, no speeding violations in the last year? The key word in this probability problem is or. When you hear this term or either in a probability problem of this nature, what you're asked to find is the union. What is the probability that a person wore a seatbelt, which is represented using the symbol wore a seatbelt C? So that's the probability of C union because of this word in here, or if we had either, it would still be a union. So we're asked to calculate the probability of C union. So had no violations in the last year. What is the probability that a person had no speeding violations in the last year? The total for having no speeding violations in the last year is given there, but the symbol is B for no speeding violations. So what we're asked here to calculate is the probability of C union B. The union means or either. So what this is saying is, what is the probability that a person had wore their seatbelt, which is C, or, which is the union, had no violations last year, which is B. And so to calculate the probability of the union of C and B, we will use the general formula, the general probability formula. And the general probability formula here is going to be the probability of, it's going to be the probability, it's going to be here, the probability of C plus the probability of B, take away the probability of C intersect B. So let's fill these in now. The probability of C, remember C is the event wearing a seatbelt. The probability of C would be the number of observations for C divided by the total number of elements in the entire sample space. So this will be the probability that a person wore a seatbelt. We'll fill in the numbers shortly. And the probability of B, where B is had no violations in the last year, will be the number of persons in B over the number of persons in the entire sample space. So this problem really brings out a lot of understanding of the principles of calculating basic probability here. And then for the probability of C and B, we need the number of observations in C and B together all over the number of observations in the entire sample space, which is S. We're using S to represent the sample space here. And now we're going to do the math. What is the probability of C? It's the number of observations in C, which is the number of persons who wore a seatbelt overall, divided by the number of persons in the entire sample space. So how many persons wore a seatbelt here? It's 146 in total. And that's the figure that we need here. 146 persons wore a seatbelt divided by the total number of observations in the entire sample space, which is this 258. As I indicated, when you're working problems from tables like these, you're always going to be dividing by the total sample space unless you're calculating conditional probability as exemplified in number 3. So this will be 146 divided by 258 plus the number of observations in B, where B is the number of persons who had no violations last year, the overall number of persons who had no violations. And the overall number of persons who had no violations is 190. So that's the total for that column, no violations. So it will be plus 190 divided by the number of persons in this sample space, which is 258. Take away the number of persons who meets the condition for both of these events. That is the number of persons who wore a seatbelt and also had no speeding violations, which is what this numerator here is saying. The number of persons who wore a seatbelt and had no speeding violations. The number of persons who wore a seatbelt and had no speeding violations is 123. This 123 here represents the number of persons who had no speeding violations and also wore a seatbelt. So those two conditions are satisfied by the 123. So we're going to take away therefore 123 divided by the number of observations in the entire sample space here again, which is 258. And so that's how we calculate. This intersection here of the two events represents a joint probability because we're calculating here the probability of two events taking place together, which is wearing a seatbelt and having no traffic violations. The intersection is read as and, while the union is read as or. Now let's simplify this problem. Because we have a common denominator here of 258, we can just write down that common denominator of 258 and simplify the numerator. Simplifying the numerator here, we'll get 146 plus 190, take away 123. So all we need to do now is to simplify the numerator and divide that result by the common denominator. So this will be therefore 146 plus 190, and we're going to take away 123, and that's going to give us 213. So this is going to be 213 divided by 258. So 213 divided by 258, and 213 divided by 258 here, rounded to two decimal places, is going to be 0.83. 0.83 is, of course, in percentage form, 83%. So what this answer means is that there's an 83% chance, right? There's an 83% chance that a person selected at random from this data set either wore a seatbelt or had no traffic violations last year. So these kinds of probabilities are very important in understanding complex data sets and in making sense of complex data sets which have multiple variables, right? So this is or 83%. So understanding this kind of information can be very useful in various situations where you're working with the intersection of multiple events, as in this case. And that is my illustrative video here on the fundamental principles in calculating probability. Much more to come, so I'll be doing another illustrative session on this, following up with further demonstrations of how to calculate basic probability. I hope you found this video very useful. Remember to like, share, and subscribe. Thank you.